Good afternoon, everyone. Happy Halloween, and welcome to another episode of Innovation Insights, where we highlight key contributions from members through their technologies. So just a reminder of the IACMI vision and mission statement. Our vision is improving everyday lives through the power of composites. Our mission is to convene, connect, and catalyze the composites community to accelerate advanced composites design, manufacturing, technical, and workforce solutions to enable a cleaner, more sustainable, more secure, and more competitive U.S. economy. Just remember those three words: convene, connect, and catalyze. And that's done through a number of ways, a lot of interactions. And since we're running a couple minutes late, I'll breeze through this a little bit. It's been a busy year so far. We saw a lot of you at JEC in Paris, at SAMPE in Charlotte, our members meeting in Utah, the SPE ACCE in Detroit, IMTS in Chicago, CAMEX just a week or so ago in California, and we will be at the Carbon Fiber Conference in Greenville, South Carolina in 2 weeks. We'll also be at the Defense Manufacturing Conference for those of you that want to go. Also, we've also had a number of working group meetings this year with our 5 working groups, and hopefully you've been able to participate in those as well. All of this is being recorded, and all of the previous webinars, Innovation Insight webinars, are on our website. So if you see something you like, you want to go back and look at it again, or you want to refer it to a colleague or something, please feel free to send them to the IACMI website, and they can get to anything. So great lineup for today. We got Andrew Bader from Advanced Additive Engineering Solutions, Reyes Baeza from Rossini International, and Dr. Hendrik Meinke from Volkswagen of America. So we're going to start with Andrew, and I will stop sharing and turn it over to Andrew. You can get to it. So Andrew.
Okay.
There we go. Can you hear me? Okay. Very good. Kim and Dale, thanks for having me. Can you see the presentation?
Yes, looks great. Thanks, Andrew.
Great. Awesome. Yes, thanks for having me again. Andrew Bader, Vice President, Co-founder at Additive Engineering Solutions. And today, this is pretty timely because we just talked about this at CAMEX a week or two ago on large format additive manufacturing for applications beyond tooling. For anyone who has kind of followed this space, tooling has been kind of the main application that's been worked on over the last several years. And I've got some, kind of exciting newer applications beyond tooling. So just kind of real quick, who is AES? So we're an advanced manufacturing company and leader in large format polymer additive manufacturing, or as we refer to as LFAM, and traditional CNC machine solutions. So we were the first contract manufacturer to offer these kind of services in the world back in 2016. As you see here in this picture, these are large 3D printers, and I'll kind of give the quick background story on those. But today we currently have the largest capacity of these large format polymer printers with 4 of them. So what do we do with our printers? Like I had mentioned, tooling and molds was kind of the main focus when we first got started. It is still a large majority of what we do, but we're starting to branch out into other really exciting applications, right? When people think of 3D printing, tooling and molds, prototyping is kind of the 2 main things that come to mind. But today we're going to talk about end use products. So parts that we're directly printing and sending to customers, not as a prototype or a tool or mold, but as an end use part. So I'll describe what is large format. Everyone kind of has different ideas of what large format 3D printing is. It's large format polymer extrusion. It's not metal, it's a thermoplastic. And where we play in with composites is it's a thermoplastic composite. So all of our material is either filled with a glass or carbon, or both, chopped, typically, format. So we measure everything in feet or meters, right? Our largest printer is 20 feet long. So we have really large build spaces and volume to print within. And our deposition, that is measured in pounds per hour. So, we're printing, depending on the resolution that we're printing at, anywhere from 5 pounds an hour to 100 pounds an hour. So we have a large variation in the amount that we can deposit, but we can print very large physically and very fast. So this was introduced commercially back in 2015 by Cincinnati in conjunction with Oak Ridge National Labs. They just thought, hey, why not take a desktop 3D printer and make it very large industrial scale? So, back then FDM printers were, 3-foot cube up to 1 pound an hour. And like I'd mentioned, we have a handful of these BAM printers. Our largest is actually 20 and our other ones are 12 feet. So definitely a step up, but that's what we mean when we say large format AM. So here's just some large parts that we've printed, showcasing physically what large parts look like off of a large printer. As I had mentioned, tooling was the main focus that we got into, and here's some pictures of tools so people know what those look like off of our printers. How we process a tool is we print it and then it's post-machined, so it's nice and smooth and accurately dimensioned. So we're near net printing and then finishing on in our CNC department to make a tool. So again, just a couple examples of tools that we've done. So for today, I've got 2 case studies to show some exciting new applications that we've been working on for end use parts. One is for autonomous underwater vehicles, AUVs, or a robot submarine. And the other is for military training systems, flight simulators. So 2 very different things, but kind of equally very interesting and exciting. So we'll dive right into the Dive Technologies project, or they were recently bought or acquired by Anduril Industries, a kind of a newer defense company in the space. And the background on what we did here was, Dive Technologies was a startup out of Boston back in 2018. We got started in 2016, so we're kind of 2 startups actually helping each other out on this project, which was kind of neat. And the founders wanted to create a safer, smarter, cheaper, but very highly customizable AUV. And that was kind of the key point there. So they came to us because they needed to print, or they wanted to print prototype fairings, right? The fairing or the shell of this submarine. So it's not a pressure vessel type submarine. It's a flooded sub, so water does flow through it. So we don't have to worry about pressure when it's 3,000, 4,000 feet under the ocean surface. So as everyone likes to think, oh, let's prototype using 3D printing. So that's why they came to us. Makes sense. So the hull of this AUV was 19 feet long, 4-foot diameter. So when you want prototypes, you want additive manufacturing. So here's a picture of us starting to print some of those large fairings. We did those in sections, several sections. So, the parts were about 4-foot diameter, but they were maybe a few feet tall. So we did several of them to connect them all together to an aluminum frame to get this prototype. So prototype fairings, we got those done. They really liked them, worked out great. They need to provide a proof of concept. They want something to, form, fit, and function and play around with on their first prototype. But now what? Once you go from prototypes, and you start thinking about production or more volume, you generally think molds, right? That's kind of the next logical step there. But there's some challenges there to molds. So traditional fairings could be done from, fiberglass layup, thermoformed thermoplastic, which both need a large investment in tooling. Well, there's a problem with that. What if you're not ready for a design lock, right? What if you're still figuring this out and, your whole mantra of your business is to provide highly customized products? Tooling, unfortunately, doesn't really help with that because you don't want to spend several $100,000s on new tooling every time you make, a new design change or whatnot. So you keep on 3D printing. As you see here on the right-hand side, this is just part of our shop being filled with a bunch of thermoplastic composite 3D printed fairings for their AUVs. And here are some of the realizations that we came to when printing these parts for actual production. So performance. When they got our 3D printed prototype, what led them to wanting to keep printing was they did test on the prototype and said, you know what, I think these panels from the 3D printer would work just as well as, a fiberglass layup or a thermoform part. So they functionally worked out very well. And what's so great about thermoplastic composites is there's so many different types of materials to choose from. You can tailor the material to what you need, right? Impact resistance, this is going to be in the ocean. It needs to be rigid yet flexible. UV stabilization from UV from the sun exposure. So that's kind of the power of thermoplastics. We're able to kind of mix and match different materials to create something that works well for them. Customization is obviously, the big one here, right? Design changes can be made incredibly quick with a very low cost impact, right? It's some engineering time to kind of redesign, but the printer doesn't realize, what's a new part. It'll print what you tell it to print, right? We don't have to go and change molds or fixtures or whatnot. It's very simple and quick to do. So an entire fairing set, the speed can be printed in as little as a week, which, if you had to contact your fiberglass supplier, they're going to have to pull the molds off the shelf, get the molds ready. And to do all of these would take multiple molds. So, when you have that full concentric fairing, you likely might not do that in one mold. So you'd have several molds to make all this. It would definitely take you a lot longer than a week. Flexibility. So additional parts can be printed on demand instead of tying up cash in a bunch of inventory, right? So when you call up your fiberglass supplier, they're probably going to want to make more than one set at a time. It's just not economical to only make one set. They're going to make several. With 3D printing, you have a little more flexibility. If you need a new set and it takes a week, or let's just say you break one part and you need a new part. And again, instead of just pulling one or two molds off the shelf and prepping those and laying up, you can just print a part, just a single part. And that can just take as little as, 8 to 10 hours to print one part. So if they need something quick, we're able to respond quickly and do that through the power and the speed of 3D printing, which is really great. So that was Dive Technologies. That was our production fairing printing, which we're doing right now. And since we started doing that a few years ago, we actually have a handful of other customers who have come to us for AUVs. AUV is kind of a new expanding market. There's a lot of startups in this space, also a lot of legacy mature OEMs that are also getting into the space and realizing that 3D printing of those fairings is just such a home run. So the second case study I have here, I think I've got about 4 minutes or left here, but the last case study is something completely different. This came from L3 Harris, who is now part of CAE. CAE makes, they're well known for making simulators, whether that's for commercial aviation or defense. But they came to us originally because they had a large order for F-16 flight simulators. What they were ultimately looking to do was reduce cost and time. The order was a little bit unusually large for them. And because of that, that was driving a really long schedule. So they wanted to see, hey, what can we do with 3D printing? Does it make sense? This is a smaller base simulator. As you can see here in this picture to the right, it's just about the size of the cockpit where the pilot would sit. So, roughly 6 by 6 by 3. And then it's placed in this 360-degree projected geodesic dome, which is pretty neat. So they kind of get 360 view all around them without using like a VR headset. It's just right there. So the frame as is was constructed from aluminum. There was fiberglass, welded together, bolted together, bonded together. And with all the nuts and bolts and washers and everything and all the individual pieces, it came out to about 3,000 individual pieces just to make the frame that everything would get bolted and assembled to. So it was a pretty large, bill of materials there. Lead time of several months. So we kind of took this classic additive manufacturing problem solving approach, which was we had the ability to redesign an existing product from the ground up to take full advantage of LFAM. So designed for additive manufacturing. Many of you might have seen people take parts and just print them on a printer. That was no different than how they were maybe cut on a CNC. But anytime you can, get a blank sheet and say, hey, take this existing product and completely redesign it to take full advantage of 3D printing, that's where you're going to get the most benefit. And we were able to reduce the parts from 3,000 down to 300. So it was a massive part reduction effort. And several months to about 6 to 8 weeks to make one of these. And then every couple weeks after that, we could produce a second, a third, a fourth, etc. So I'm going to go through some pictures here. So as you see here, this is the base of the frame. On the right-hand side is the completed print. There's a few more layers left, but right in the middle is where the pilot would sit. So they would put a seat right there. And then we printed 2 more pieces, which were these side pieces on the left and right, and those would go on top of the frame. There was a lot of machining that we did to this project to make it work, for all these cutouts, for them to put their electronics, dashboards, things like that. Just some more pictures. And here is the completed cockpit frame that we did. So it was machined in the places it needed to be, places where you wouldn't see, or they would get covered up by other panels or whatnot, would be left untouched. So, you don't want to have to machine things that don't really need to be. So we keep everything as economical as possible. So the results from this are pretty obvious, but we'll go through it here. Is from a project management perspective, imagine the difference dealing with a 3,000 piece bill of material down to 300. Just a massive reduction in project management. Just aside from the manufacturing cost, there's a bunch of soft costs as well on top of project management. Was general engineering. If you're an engineer and you have to have drawings for all these different pieces, again, reducing that part count is a huge cost and time saver. Same with purchasing, right? If you have to purchase all those pieces from, a dozen or so different suppliers, and you're now able to reduce your supply base because you have shrunk that part count down. And then speed, 4 to 6 months down to 6 to 8 weeks. That frame that you saw right here printing, this got done in about 14 hours. So in about a day, you had this frame fully 3D printed, where something like this would, take someone probably water jetting or laser cutting aluminum plate to all these different pieces. And then they'd have all these weld fixtures to put together and weld it all together. Just a lot of work involved, but something like this took 14 hours to print. So yeah, that's the end of my presentation. I think I had about 15 minutes here. But these are two really exciting applications that are showcasing how we are now dealing with directly end use parts, right? These cockpit frames weren't a prototype, they're going on the real thing. So really exciting. And thanks to IACMI for having me on to showcase these new applications we're dealing with.
Thanks, Andrew. We had a glitch there where I was unable to unmute. So I want to make sure that everybody else is that's speaking here. We don't have any questions right now. Plus, we're running tight on time. But I'm going to put a question in the Q&A. I encourage others to as well, and then you can monitor that and respond during the rest of the.
Sounds good.
The webinar. But really cool to see some applications outside of the tooling space. Okay, we're going to move on. Our second speaker today is Brosius Baeza. He's a composites manufacturing manager for Rossini International. And if you've been paying attention, Rossini's developed a lot of new applications in composite space, a traditional supplier of suspension equipment. So Brosius, it's let you share your screen and we'll get started.
Sure. Can you hear me, Dale?
Yes.
Perfect. I just wasn't sure if I still had the problem with the unmute. Okay. Let me just show my screen now. And can you guys see my screen now?
Looks perfect.
All right. Well, first of all, thank you very much, Dale, Kim, for organizing this and for having me over for the invite. And they already introduced me, but I'll do it again. My name is Brosius Baeza. I am a composite manufacturing manager, so I'm head of the composite manufacturing facility here in Rossini. We are based in Piedras Negras, Mexico. And today I will be showing you our capacities in our plant and different projects that we have been working on. So a quick overview of who we are, Rossini. So let me just minimize this. There you go. We are a $1 billion company regarding the revenues from 2021. We have more than 6,600 employees around the world, 7 plants, and 4 main operating divisions. We got leaf springs, we got brakes, we got coil springs, and we got elastomers. Here is a view of some of our products. We have leaf springs for light, and we have also for commercial trucks. And we got coil springs for light vehicles. We got discs and drums for light vehicles as well, and rubber and metal bushings for suspensions. Here's a quick view of the different variants of our customers for leaf springs. So we got our commercial vehicles that they normally use Link Omega springs. They use Air Links with main support members, high stress single stage leaf springs. We got Super Duties, which use single stress or multi-leaf suspension systems with either 2 or 3 different stages. We got light pickup trucks, normally with 2-stage springs, and also the progressive monoliths. We got vans also with 2 stages leaf springs and also some transversal. And of course, we have components made of elastomers for anti-vibration. Regarding the light weighting of these leaf springs, if we use a base of a conventional leaf spring, we call them a 2P plus H. So this means that we have two main plates, as you can see it on the picture, and we have a second stage, which is a steel helper spring. So for this one right here, if we replace the steel helper for a composite helper, we managed to reduce 10% of the whole assembly. But if we replace the main plates, the two main plates, with one parabolic for higher stresses, and we make it a full steel, we will be able to achieve a 20% weight reduction from the base one of the full steel to P plus H. And if we move further, as we did with the F-150, changing the helper from steel and turning it into a composite, we were able to achieve a 35% weight reduction in the assembly for this particular product. Of course, you can take it further, and we can make, instead of a two-stage, we can make a progressive steel monolith, which will turn into a 45% weight reduction of the assembly. And if we turn that one into a composite, it can go as low as 60% of the mass reduction, right? We have also worked with transversal springs. One thing I did not mention at the beginning is that Rossini is not only designs or manufacture, but we also help with the development with our customers so that we can do all our trials in-house. So this, for example, this is an example of a transversal spring in our mechanical lab, where we do our testing for deflection and all the characteristics that we need to make sure that we have the right performance for the vehicle. Here's a list of our customers. You can see we supply to mainly most of the major OEMs. And of course, also we have some cases where we supply as a tier 2 for the whole assembly that is supplied to the OEM. Now, for composite manufacturing, here's a look at our spring that is now in production. This is the F-150, and this is the award-winning technology that we had in the last couple of years. So as I mentioned before, it's a main steel plate where we replace the composite helper, and we managed to reduce it 35% of the whole assembly. And with this, we were able to get a couple of awards. So we got the Altair award for the lightweight module category. This was in 2021. And also we got a couple of awards from SPE, also with this same technology. Right now, our composite facility is the largest HPRTM facility in North America. Just to give you an idea, and of course this will depend on the shape of the parts and dimensions. We are a little bit short of 1 million parts per year in our capacity, and we have 3 fully automated production lines where they are divided into different centers. We got our preforming for all our fabric handling. We have our 1,700-ton presses where we do the resin transfer molding and high pressure. And we have machining centers at the end so that we can do all the features like the drilling, the milling of all the components, so that we have a proper part for the assembly in the end. So this is a small glance at our facility. And of course, this is very flexible because you would only need to be changing the tool depending on where you're looking into. But we managed to have our lines flexible enough so that we are not just able to produce leaf springs, so that we can actually incorporate different products. So into composite lightweighting. So Rossini, we are always looking into expanding our product portfolio. I mean, we're trying to include our composites, not just for suspensions, but also increasing our broader capacity so that we can produce different products outside of suspensions. So here's an example of a project that we worked on. Was we took an existing battery electric vehicle enclosure, a BEV. We took the part, we did our benchmark, and we made the exploded view so that we can analyze which products we could actually make out of composites. So, for example, we took this enclosure, and we decided, well, let's go and work with the tray, with the bottom tray for the whole assembly. And once we chose that one, we analyzed what material it was with the whole benchmark. And with this, we said, okay, let's try and transpose this design from the aluminum tray to the composite version. So I think there was someone trying to talk. Not, I'll continue. Okay. So then we turned this aluminum one into a CAD version for maybe LCM or also for vacuum assisted RTM. So for past prototyping, we decided to go with a vacuum assisted resin transfer molding. And we first looked into the different loads and the different scenarios where these bottom trays were going to be against you. So we did our assumptions, and we managed, with these assumptions, we managed to do our CAE analysis, where we decided which type of fabric, which type of fabric architecture we'll be using, and which resins we'll be doing for our prototypes. And we came up with a couple of different architectures of the bottom trays. Another product we looked into was a B pillar. So we did our research on how these pillars are made, what they will require, the shapes, and how they should be assembled, how is the current process, and we managed to get our hands on a tool for trials. And what we did was we took it into our prototype lab in a 400-ton press, and we did some different parts with different fiber arrangements. In this case, we did some braided fabrics. We did do some biaxial, some quadrax. We did carbon fiber, we did basalt. All the different variants that we wanted to look into so that we can actually have a pretty good business case. And this process is also, we did it with LCM, or liquid compression molding, or wet compression molding, just to make sure that we could explore also those processes, and because of our assets that they are able to do this process, not just HPRTM. And last but not least, we're also into SMC trials. So right now, with the tendency for the battery covers, we were looking into the applications where the SMC could be applied to. So we took one existing as well, battery cover, and we did some trials with different materials. We did vinyl esters, we did epoxy fiber resistances, we did epoxy with carbon fiber, glass fiber, phenolics with glass fiber. And for sure, the next steps for this ones are the full characterization and make sure that the performance of these parts are meeting the new standards that are for the flame resistance. This would be the end of my presentation. Of course, if you have any questions, I'm happy to answer them. Otherwise, or if anybody wants to discuss any other topic, I'm open to discuss after the meeting.
Thanks, Reyes. That's great to see all these various applications that you're working on. How close do you think you are to being able to do a single monolith composite spring? I mean, they've been done in the past, but then they disappeared. So.
Right. So the let's say a monolith, we have already done them. We have already some trials, and they are successful. Right now, the ones that we have in development, and we have also very good results, are the progressive ones. So we're not very far from them. Actually, we have working prototypes. Right now, it's just a matter of the right project so that we can actually take it to full production.
On the B pillar,
right.
Look like you're trying to do the whole pillar rather than just thin out the steel and do an insert like BMW and some others have done. What are the trade-offs there? Because obviously one of the big issues you've got is how do you join the pillar to the vehicle?
Right.
Doing all composite pillar.
Right. That's a good approach as well. So firstly, what we wanted to do was make sure that we could get into different products, not just for suspension, right? So that's why we decided let's try with our own assets different manufacturing processes, and this pillar was something we could get our hands into. But of course, there are different approaches. I mean, just like you mentioned, it's maybe just replacing some components for another ones, or just using the composite as a reinforcement below the steel version for sure.
So if anybody else has any questions, please put them in the chat or the Q&A. And Reyes, I would ask you to look at that and see if some get in there, and you can answer those during the next session.
Sure.
And, thank you again for your contribution.
Thank you guys for having me.
Great progress. Okay, our final speaker for the day is Dr. Hendrik Meinke. He's the project lead at VW's Innovation Hub in Knoxville, Tennessee. I believe Kim's going to run the presentation on his behalf, and then Hendrik will guide that. So, Kim, you want to get that started?
Sure. Let me pull that up.
And this is a two-part presentation. There's a PowerPoint presentation, and we just need to click play.
At the Scale-Up Research Facility, or SURF as we call it, we offer a unique asset in North America, and particularly in the United States, where we have a collaboration space for industry, where we work with industry closely on projects that require development, prototypes, as well as run-at-rate demonstrations.
Today, we are hosting Volkswagen Crew, and we are molding the Class A outer for the Volkswagen Atlas. We have resin supplier Ashland, CSP, with IACMI Purdue. IDI is committed to collaborating with industry partners to advance, the world and bring what we can to the table.
Hendrik Meinke, I'm leading the product innovation team for Volkswagen here in the North American region. And IACMI gave us the opportunity to formalize this relationship, and also having the connection over IACMI to all the suppliers, the complete supply chain, beginning from material over simulation up to prototyping, is a great opportunity for Volkswagen. And so we want to show how composites can help lightweight our vehicles. Here we are replacing a steel liftgate with a SMC composite solution, which saves around about 35% of weight in the vehicle. Another big point is the Class A surface we want to accomplish in this project. Making the prototypes helps us to demonstrate all this goals and accomplishments.
The molding process starts with your material. So you cut a blank charge that is typically flowable, so you have significantly reduced waste in the process. So then once you have your charge, it's placed in the mold, then you close your mold and you apply tonnage. So under tonnage and temperature, you start to cure your part, you flow and fill the part, and you get a fully cured part once the cycle's over. Compression molding offers you the ability to mold thermoset resin systems that offer high strength and high heat stability and a greater design flexibility than you get with metal stamping.
I think it's pretty unique what we're doing here. That's something what IACMI made possible, really from material up to the prototype. Everything is basically available in one institution.
There's a lot to be out here and represent my company and work with great people. Great opportunity to be a part of stuff like this, where you're changing the world. That's what we're doing.
Send your friends and family a party in a box from Harry and David. Nothing turns a good time into a great time like a box.
Thanks, Kim. Hendrik, are you able to talk now? Hendrik's having an issue here.
Yeah, he's unmuted, and I'm not quite sure. I know that he's had some issues with the Zoom earlier today too.
Why don't you can you pull up the presentation?
Sure.
I have to, I'll deliver it on his behalf. Okay, you go back to slide 1 and then do Control L.
Yep.
Yeah, he's struggling to get unmuted. Is there a call-in number for that he could do?
I will work on that if you want to start.
You know, you got his number, you call him. We could just play his audio through the phone.
I'm working on that. Sorry, everybody. I appreciate your patience.
I'm calling him. Then what I'll do is I'll just put him on speaker and let him.
You're calling him? Okay, thank you, Dale. You got to his number quicker than I did.
Hendrik. Okay. I'm gonna let you speak to the presentation, and you can advance the slides that way.
All right, yeah. Can you guys hear me okay now? I'm connected by phone now.
Yeah, can everybody hear him?
Yes.
Okay, you're good to go.
All right. Oh, sorry for this delay here getting started, but it seems like Volkswagen IT is not that good with Zoom, so usually we're using Teams. So yeah, let's get started. With kind of 10 minutes left, I will kind of rush through the presentation, but yeah.
We've already played the video, so you're good.
Here.
So go to the next slide, Kim.
All right, here, quick introduction to Volkswagen Group of America. Yeah, with the brands Volkswagen, Audi, Bentley, Lamborghini, and Bugatti, we are present in the American markets as well as Porsche cars and Ducati. And yeah, this project here will focus on the Volkswagen class. Yeah, let's move to the next slide. So it's a Volkswagen Group Innovation Hub in Knoxville, where we presenting from today. And we are part of the Volkswagen Group innovation ecosystem with Innovation Center in Wolfsburg at our headquarters, Innovation Center in Asia, and Innovation Center in California. And basically each innovation center has innovation hubs connected to them with specific topics, and in Knoxville we are mainly responsible for sustainability and innovations in electronics. Next slide, please. Yeah, you see the focus areas where we working on in Knoxville. You will hear from the first focus area today, a cost-effective composites. We also working in functional materials for battery electric vehicles, like new power electronics, wireless charging, to name here. And the third really important pillar, circular economy and recycling. Also focus of IACMI 2.0. But yeah, let's get into the cost-effective composites and the liftgate for the others. So here, quick motivation. What was the motivation for this project? Basically, what you see since several decades in the automotive industry is basically this wage bill. You know, you get more safety, more convenience, more quality, even with the e-mobility and the weight of the battery, all the sensors for self-driving cars and stuff like that. Basically, since several decades, the weight scroll only knows one direction, and that goes upwards. All the features we're putting in the car's getting heavier and heavier. And what we're trying to address with some of this project, like the composite liftgate for the Volkswagen Atlas, is basically reversing this weight spiral. So if we can component functional integration, make some of our components lighter, that basically leads to a trickle down effect in the weight spiral, and hopefully we can at least kind of reverse the weight spiral. Moving to the next slide. So this Volkswagen liftgate project has been a pretty big project. The official title was Reduction of CO2 emissions through lightweight body panels. Basically, you see all the targets. We for sure wanted to fulfill conventional specifications and requirements of this part. The target was a similar weight to an aluminum version of the liftgate, but the part cost should be way lower than aluminum. Reduction in investment cost was one of the targets as well. High volume capabilities, so we're producing over 100,000 units a year, and for sure the Class A surface quality. To make such a large project happening, we had a number of strategic partners here. We worked with Oak Ridge National Lab and IACMI here in Knoxville as well for material development. We partnered with University of Tennessee for design and simulation with Purdue University, and for the prototyping with MSU in Michigan. We had Owens Corning and Ineos, which was still Ashland at that time. We ran the project for materials, IDI for compounding, and for helping us with design and prototyping and tooling. CSP was part of this project, which is page in now. Basically the goal was to develop a full-scale demonstrator in collaboration with all the partners to demonstrate this technology is ready for high volume production. Let's go to the next slide. You see here the list of testing and details. Maybe I will kind of skip through that a little bit since we are really tight on time. But you see what has been all done in the area of material development, and basically really to make sure we create a material which is Class A capable, and also being capable for e-coating, so that way we don't have to change anything in our assembly line, and just can mount the liftgate in the body shop and run it through our conventional paint system. Next slide. You see our design process, mainly driven by Purdue and also supported from CSP. So basically, we started with the current steel design, redesigned it in CATIA for the composite application, predicted fiber orientation with Moldix 3D, integrated material properties finally with Digimat, and also then have a predicted manufacturing informed performance with Abacus. So really this kind of approach was led by Purdue, and after several iterations, we went to the final design and also to the tooling. Next slide. Show the production process. So like you already saw in the video, it starts with the molding that has been done at SURF using the shooter press and the SURF facility from IACMI. Then we did the trimming at shade process. Automation bonding was supported by Excel. The priming of the parts for being ready for the E-code in Chattanooga was done by CSB in the Antican plant. And yeah, finally then the parts have been painted at the Volkswagen facility in Chattanooga. Next slide. So basically, a quick summary. You see the current steel design on the left-hand side and the full SMC design on the right side. Really an impressive result in consolidation in part count reduction from 10 to 3 parts, weight reduction over 36% from 21.1 kilogram to 13.6 kilogram. And like I said, this really no change in assembly sequence needed. We can paint this lift gates in our paint line like we would do for steel lift gate. We achieved dramatically reduction in capital investment and for sure also in F time, since only 3 parts needs to be assembled instead of 10. And that's kind of completes the presentation with 1 minute left for questions.
So I've got a couple. So obviously you ran a bunch of vehicles or some vehicles through the E-coat line and full paint line in Chattanooga, and then you put some in the field for testing. Is that testing complete, and how did that go?
So the open air weathering is still going on in our proving ground in Arizona. So far everything looks good and promising, but yeah, that's testing as well.
So what's the likelihood this technology finds it on to the next generation of Volkswagen vehicles?
Well, we have already several vehicles who got influenced by this project. So you will see, for example, the Volkswagen ID bus coming to the US beginning of next year, which will have a composite lift gate. Also, the new electric compact from Volkswagen, the ID3 has a composite lift gate. So there is some influence which resulted from this project. But since the Atlas right now is in production with the steel lift gate, this probably has to wait for model change in Chattanooga to implement it also.
Yeah, right. Okay. Well, appreciate that, and thank you, Hendrik, for working through this. Hold on, we got one question. I guess we have a question. We'll get to that right now. Is structural integrity equal or better than the steel lift gate?
Yeah, from a mechanical performance, we fulfilled all the load cases, same as the steel lift gate. So there was no compromise on performance and spec for composite lift gate. Yeah.
Right. So all the torsional things you have to do in the load cases, it passed all of those.
Exactly. Yeah.
Okay. Excellent. Okay. Well, it's 1 o'clock. We've managed to make it through. We appreciate. Had a few technical glitches with Zoom today that happen occasionally. And you've all seen them the last couple of years. So we will again thank you for your time today. And this episode, including all the glitches, will be has been recorded and will be available on our website following. So thanks to all of you, and we'll see you next time. Happy Halloween.
All right. Thank you, everyone.
Thank you.
Thank you, guys.